All right. Let's go ahead and get started. Hi, everybody. How was your Thanksgiving break? Did you have a good time? Awesome. For those of you who came in late, I'm in consideration for a new reality show. And so we have these cameramen here. They're here. It's all about me and looking good on the camera for the show. It's called something like Extreme Survivor or thing like that. I don't know. It sounds pretty cool. Anyway, so they're going to be here. They're going to sneak out after a little bit. Any questions on the project so far? You should have been making good progress by now, I imagine. Those of you who have started. Who started? Who is lying? Just checking. Okay. Who hasn't started? Yeah, okay. I'm sure you won't have any problems getting it done in 2 days. Any questions about the project? Yes? Mm-hmm. Yep. Okay. The data checking function that is in the subject class just does the range checking that we've been doing elsewhere. So essentially when you call that method, say check the range, it goes through and it looks at everything that's been loaded in and just decides whether everything is in range or not. Nope. You've already done the input at that point. Because now we're doing the input through the overloaded operator. And the overloaded operator is not doing any error checking. So we're just dumping all the data into the subject straight out of the file. So after we've done that, at some point, we need to check and make sure the stuff that was loaded in was good or not. Does that make sense? So the overloaded operator does the input into each subject. Once each subject is loaded in, you can call check the data on that subject. And when you call it, it goes, oh, I have data that's been loaded into me. Let me see if the data that was loaded in is within range or not. So within the subject, so there's two things, and I don't remember the name off the top of my head, but there's one in the subject class, right? Reynolds subject class, which is like check data. And there's one in the cohort class, which is like check cohort. I guess I named it something like that. So the individual one for the subject just checks the data inside the subject. The one inside the cohort goes through the linked list, and for each one, calls that individual one to see if the data was good for that member of the linked list or not. Yes. And checking the cohort is going through the linked list and checking every subject using the thing that we did before. So for this project, in case you were bored and have too much extra time, there is additional thing you can do, which is the delete bad subjects. And if you want, you don't have to, there's no extra points for it. If you want, you can run the command that will go through the list, find all the bad subjects, and remove them from the list. No, checking cohort is not removing them. It's just going through and checking each one and telling you whether they're bad or not. So, but not deleting them from the list. So the check one just tells you which ones are bad or not. And if you have extra time and you choose to implement it, then you can also do the delete thing. The delete is more complicated, and I haven't shown you how to delete things out of a linked list. It's there as a challenge problem if you want to figure it out. So, does that help? Okay, other questions? No? No other project questions? Going. Okay, next class. By next class, what I'm going to have for you is just like I sent out a list of topics for the midterm, I'm going to send out a list of topics for the final, either this afternoon or tomorrow morning. At the beginning of next class will be your opportunity to ask me about the subjects that is on the final, okay? So when I send this list out, take a look at it, and if you have any questions, bring them on Thursday. So now we're going to do something a little bit different. Are you ready? How many of y'all that struck fear into your hearts? Okay. We're just going to do this problem. It's pretty easy, just like we always do. All right. I'm going to give you a sheet. On the front, there's text that says some function calls. That's the one you're going to do first, okay? Go through this problem, do these some function calls. If you just take some and hand them back. And then in a few minutes, we'll go over it and see what the answer is. So. All these camera folks in the way today. You're welcome. Is that enough? I'm going to be on the show? I think maybe the title is The Even Bigger Loser or something like that. So. All right, do the one called sum function calls. Don't worry about the one on the back. How's life? Good. You programmed before? So, you know, I've been recording all this stuff for the class, and we're doing Flip Classroom. I have like a grant to do the Flip Classroom stuff. Oh, you got one. And those are the people who are on Candles, which is a center on campus, which is developing new technology, and they wanted to come and see what I've been doing during the semester. Pardon? Oh, they're mostly interested in like the AV setup, like how I set up my computer and all the stuff I do in my office to prep my equipment before I come over and stuff. And for some reason, they wanted me throwing candy at you, so that's what we did. So feel free, talk amongst yourselves, work together, help each other out. We'll do this for maybe 5 minutes. This one's a little bit complex, maybe. I do, but you're late. Should I give you some anyway? Should I give you some anyway? Can you hand that back? Shoot your haircut? I like it. Looks good. We're doing that one on the front, some function calls. Why are you sorry? I don't know why everybody else is being quiet. You should all talk. It's fine. I encourage it. turn the sheet over. Oh, no. Any extra sheets floating around somewhere? Ah, thank you. I thought I had made enough. All right, we'll take about 1 more minute. Doing the one called sum function calls. Oh, you got one? Did you get one, Tommy? Judith? Okay. All right, I just want to make sure everybody got some. All right. How about we go ahead and figure out what this is doing? Anybody want to step me through this code? You're very brave. Go ahead. So we start with main. Okay, so we call main, we set x equal 3. Now we run the function 1. So we're in function 1 now. Now we're going to take ret val, and we're going to set this equal to? Okay. Yeah. Sorry, let me scroll down a little. Okay. Yep. We enter the if statement. Is 2 is greater than 0? So what do we do? So now we have to run 1 again. Wait a sec. Parameter equals 2 when we come down here, right? And then we decrement and make it 1, and then we run it. Okay. And so now we have to go over here. We enter 1 again. Great. Okay, everybody followed this so far? Right? We just called main called 1, 1 called 2, 2 called 1, and when it called 1, it called a different instantiation of 1, right? It doesn't like somehow go back. Each time you call it, it creates a new version. And what I've drawn here is kind of how we step through it. So finally, we've come down to this case where there's a parameter and it says 0, and then what do we do? All right, and so parameter now, this thing ret val gets set to whatever is returned. So it was 0, and it's being reset to 0, so it doesn't effectively change. And then what happens? Uh-huh. Yep. And then what? Yep. Then we go back to this 2. Right? So we went from 2 to 1. We go from 1 back to the other 2. We go from this 2 to where? Everybody with me? So each time, so you might have think that it only prints out exiting 1 with exiting 2 with 0 and exiting 1 with 0 once, but it's going to print it out multiple times. It's going to print it out each time it comes back up through these series of calls. Does that make sense? Because each time we call it, so I'm actually gonna run the code so we can actually make sure that we haven't made some sort of gross error. And here's what you can see is it enter, 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 exit, 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 exit. So it went enter, 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 exit, 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 exit. Because each time you call one of these functions, it is a separate and distinct instantiation of that function. I see a lot of people who look perplexed. How many of y'all are perplexed? No? This is the exact same code, isn't it? Why? What did I do completely wrong? This is, sir. Because what's happening is we come into 1, it see out something, and then it makes this function call. So before it reaches this exiting, it has to go do this function call. And then it reaches this function call and it prints something out, and it has to do this function call. So it goes back here and it enters this function call. Then it has to go down here and it enters this function call. So because this function call inside each of these is surrounded by the print statements, each time you enter, you'll get the print statement, but you won't get the exiting until the function that's called in there returns, which it hasn't yet. When it's coming back, each time we've done this in function 1, we've initialized it to 0, right? And each time we return, we're actually changing the value from 0, right, which is right here, ret val equals 0. We're changing ret val from 0 to whatever this returns. That just happens to return 0. So each time we're changing ret val from 0 to 0. Mm-hmm. Yes, incoming is different inside each one. So here's the first function 1, incoming is 3. Here's the second, incoming is 2. Here's the third, incoming is 1, which is what we print out, right? Enter 1 with 3, enter 1 with 2, enter 1 with 1. Yes, because this is always returning 0, right? If parameter is greater than 0, we're going to go do something, but if it's not greater than 0, it must be 0 or negative, but we never actually reach making it negative, so it's always going to be 0. Right. And then 1 as well. When it returns back here, ret val is going to be 0. It'll print out 0. Yes? The third time of what? Uh-huh. So let's count. It entered 1 once, twice, 3 times, and it has to exit 1 that many times. Once, twice, 3 times. So every time you enter a function, you have to exit the function. That's right there. Uh-huh. Yep. Right. Every printout you see is happening. I'm not quite sure I understand your question. Yeah. Yep. So this, what happens is when we return from 1, it's going to set parameter to 0 each time. So I kind of skipped. I didn't go through the example completely because I would like to go on to the next one. But here's what happens, right? Parameter is 0. It returns that. Ret val is 0. It returns here. Parameter used to be 1. Now it's 0. It outputs 0. It pops back to the next one. Ret val now becomes 0. It outputs it. It comes back here. It changes that to 0. Ret val parameter 0. So it returns. It changes this from 0 back to 0. And then when it returns to main, it doesn't print anything out. All right. Now you're all looking at me because each time we're setting this equal to what the functions return. And on the way back, we go from 1 to 2 to 1 to 2 to 1 to 2. And when we're done, 2 is always going to return 0. And each time this equal sign, it's going to set parameter equal to 0, and then it's going to set ret val equal to 0 each time on the way back. Every different instantiation of 2 has a different value coming in, but just like we changed things in 1, we are now changing things in 2 with this equal sign. So once these things start unwinding, right, once we go through all these function calls, each time any one of these function calls return either 1 or 2, they're always going to return 0. That's exactly what happens. The bottom one gets to be 0, and then it passes it all the way back up. Yes? It is possible to enter functions forever and never exit. Eventually, your computer will crash. Uh-huh. Okay, any other questions? I'm going to answer your question, and we're going to answer it in great detail later on. Okay? This is a new technique we have not yet discussed, and this is we're not quite there yet. This is the first step I like to show you on the way, where one function can call another function. Each time the function gets called, a new copy gets instantiated. Everybody comfortable with this idea that when you call a function, if you call the same one over and over again, it doesn't like magically go back to the one before, but it creates a new copy. Everybody good with that? Great. Flip your sheet over and do the problem on the other side. What? Is that kind of cool? It gets cooler, just wait. All right, we'll do this for about 1 more minute, then go over the answer. Doesn't mean you have to be quiet now. It means you have a minute. By the way, Helen. You're welcome. All right, enough people are looking bored, so let's go ahead and talk about this. Who wants to step me through this one? Emily. Uh-huh. So we start in main. What do we have in main? Uh-huh. Okay, so we call 1 with the value 3. So incoming, did I call it incoming again? No, I call it parameter. Enter 1 with parameter 3. So we call 1. And what does parameter get passed into this version of 1? So we started at main. We called function 1 once, so we got a function 1. We call function 1 again, and this time the parameter is 2. Okay, and we say enter 1 with 2. And we're all done, right? Why are we not all done? We exited. We returned. And then? And then go back to main. Okay, so if we run that, if we step through that right, we should see entering with 3, entering 2, entering with 1, and then returning, exiting with returning parameter 0, 0, 0. Everybody see how this works? When you call a function can call itself. And a function that calls itself is called recursion. Recursion. Recursion is a concept that we have not touched upon yet, but it is incredibly powerful. And let me describe it to you informally. Recursion is when you take a big problem and you slice off one little piece and deal with that little piece, and then pass the rest of the problem on to another function to deal with. Does that make sense? So you have like a big problem, and you take one little piece, and then you deal with the rest by passing it to another copy of it. The important thing about recursion is that you must have what is known as the base case. The base case is at some point where the recursion stops, and then the whole thing can unwind and start returning values. If you do not have a base case, you will just recurse infinitely. You will get into infinite recursion. And what will happen is inside your computer, there's all these copies of these functions being made. Your computer will run out of memory and eventually crash, which is bad. Yeah? The base case for this in the code is if parameter is greater, if parameter is less than 0 is really the base case. The way it's phrased here is if parameter is greater than 1, keep going, but the base case is actually if parameter is equal to or less than 0. That's when we stop and start going back up. All right, now you're all wondering, you're like, all right, you tell me this is powerful. But why should I believe you, right? How many of y'all believe me that this is powerful just because I tell you? Ha! I need your social security numbers for your grades and for my retirement. So, okay. Recursion is very powerful. I'm just gonna give you a couple of examples of recursion, like a simple one, and then we'll talk about one that's more specific to us. So anybody heard of factorial? Anybody know the factorial? How does factorial work? Five factorial. How do you compute 5 factorial? What is it? 5 times 4 times 3 times 2. Is it also the same as 5 times 4 factorial? Now, is that actually the same as 5 times 4 times 3 factorial? So this is an example of recursion. You can calculate factorial by saying 5 times, and if we wanted to actually write this function out, do you want to write it out? We'll just write one out really fast. I wasn't planning on doing this, so I'll probably screw it up. I'm over my fear of doing that because I've done it enough. But let's declare a new thing. Let's do int factorial, and it takes an int. And then down here, we will say int factorial int parameter. Okay. So in factorial, we have a base case. What is our base case? The base case is? What is 1 factorial? Okay, the base case, I'll just tell you. If the parameter is 0, return 1. That's our base case. Okay. So otherwise, what do we do? Yeah. Thank you. Here. Oh, incoming, sorry. Sorry about that. You okay? Did I spell it wrong up there? Okay, so. All right, is that going to work? So here's essentially what we're doing. We're saying if the parameter is 0, return 1. Otherwise, multiply parameter times factorial of whatever it was minus 1. Okay, does that make sense? Do you think this is going to work? Should we try it and see? So out here in our main, what I'm going to do, I'm going to get rid of this function called a 1. And instead, what we're going to say is, how big can we make this before it gets too big? All right, so all we're going to do is we made x equal to 9, and now we're going to use our new factorial to see what it comes out to be. Anybody know off the top of their head what 9 factorial is? Anybody know what 0 factorial is? Anybody know what 1 factorial is? I think so too. Okay. Did you choose a calculator? Put your hands on top of your head and tell me what 12 factorial is. I'll give you a piece of candy. Okay. All right. Apparently it's 362,880. All right? And the way this got computed, again, is this factorial thing, right? We can say, and what I'm just going to do is I'm going to put a little thing here that says recursing, and So we'll just output what's happening here, and you'll actually see, whoa, what did I mess up here? Yes. And you can see each time it's gotten a little bit smaller, and what happens is as it's figuring each thing out, like as it figures 3 factorial out, it returns it and it multiplies it each time up. Okay? This is a small example. I will tell you now, there are entire languages in computer science that essentially do not have loops. Instead of looping, you use recursion. Okay? And it's mind-twisting. There are mind-twisting languages if you've learned to program this way, which is how I started, kind of in an imperative language like this. When you get to languages that like Lisp or some other things that only really use recursion a lot, at first your head hurts, and then all of a sudden you're like, the light bulb goes on, and it's like God kissed you or something like that. You're like, oh my God, this is fantastic. And then you get out of your AI class and you never use that language again. You come back to this. So, okay, so any questions on what's happening here, right? Recursion, what do you need for it to be successful? 2 things, a base case and a problem that you can take little pieces off each way, right? Because each time you need to reduce your problem by just a little bit. If each time we don't reduce, like if we did something crazy like just did this, parameter times factorial parameter, now we have infinite recursion, and we can just see what happens. It's going to be too slow. There we go, seg fault. Eventually we ran out of memory and the program crashed. Okay? Because we made billions and billions of copies of those individual functions, and it ran out of memory and said, I give up. So, all right. Everybody kind of understand the concept here. We have a base case, and we have a problem we can slice little pieces off of. Yes? Who's happy? Who needs a piece of candy? All right, we're going to take, oh yes, you definitely deserve one. We're going to take like a break, stand up, stretch, wiggle around, do what you need to do. Sorry, I got to find one heavy enough to throw back there, Emily, because the Butterfinger wrappers changed and they're very light. Oh, sorry. It's all Butterfingers now. You're always hungry. Anyone else? Anyone? All right. While we're taking a break, I'm going to hand out one more sheet. If you'll just take a moment to pass these around, and we'll start in a minute. I'm passing those across. Let's go that way. You're welcome. I get the yellow one? All right. Did you get one of these? All right, where did the papers not make it yet? You're welcome. All right. Everybody get one of those new papers? Okay, you should have in front of you a paper named linked list something. Linked list something. Tell me what this prints out. What does it print out? I should have brought harder problems for you. Sorry. Extra sheets somewhere? They're probably over here. There. Thank you. What is what? Set next node means follow the pointer to the next box. When you reach there, call the set next node on that box, which changes the pointer that points at something else. If you have a pointer at a particular box, like if you were to call it on head, it would go here and it would set the next pointer of this to point at something that's currently. No, it changes the pointer inside the node. Yeah. To whatever the parameter is, yeah. Hmm. Good question. She was right, by the way. You're totally right about what it's doing. What's it doing? Yeah. That's the same code we did last time. Yeah. Mhm. Yeah. So set next node. Like if you have like pointer set next node, that means follow the pointer to the box at the end that's a node. When you get there, look at there's two boxes. Look at the pointer that's stored in there and change that pointer to point at something else. Whatever the parameter that's given. So it says set next node head. That means, yeah. What? You are? Okay. What? Okay, well, this isn't quite right. This code that right here is exactly the same code we did in class last week. If you were here, that created a linked list in the opposite order that was there. Right? So when this code is done, you should have head pointing at 1, which points at 4, which points at 2, which points at 8, which points at 16, which points at null. Okay. Yeah. Okay. So then you're confused about that thing. Good, we'll go over that in just a minute. How's everyone doing? How many of you are happy? How many of you are unhappy? How many of you are ready to go over this problem? How many of you just given up and you're ready to go over the problem versus how many of you are, yeah, all right. All right, well, we'll just go over it then. Quitters, come on, you can do it. All right, let's go ahead and step through this. This should be the same code you have on your sheet because I cut and pasted it earlier today. The only thing I didn't put on this is like what the values are that you're supposed to put in there. I'm going to do this piecewise. Who wants to tell me what this piece of code right here does? Yes. Yes. And is there anything distinct about that linked list that you could describe? Okay, so it creates a linked list. It adds things to the head of the list, so things that are on the list get put in opposite order, right? They get put in kind of in opposite order. So when this code runs, and if you're curious about what this is doing, we did this last class. When this code runs, we end up with something that looks like this. Head, which is a pointer, and it points at 1, right? You need to talk me through this because I know I changed the order of the numbers in there, but I don't remember what they are. Which it points at 4, which points at 2, which points at 8, right? Which points at 16, which points at nothing. So when this code runs, and trust me, you should be familiar with this code. When I send out the exam topics, I will put on there the different things that I expect you to be able to do with linked lists, and I will only write programs mostly that do those things, and I will count on you being able to recognize them quickly to be able to get through the exam in time. Does that make sense? So, okay, so this builds a linked list, and it builds it in the opposite order in which the data is input. And just like I draw it, the nodes get bigger as they go along. Okay, not really. Yes? You would have to look at the video of Professor Malouf did about linked lists, and he does that in that example. It's more complicated. I'd rather go over this in class right now. Yes? Yeah, because what's happening is every time we add a node, we put it in the front. So when the list gets built, I know you weren't here. Okay. Yeah, I'll just step through it really fast. So what happens is originally this is head, and it points at nothing. And what happens is the first one that comes along is 16, and it points at that, right? And then what happens is each time we add something new, we add the new one, and we point that at head, and then we point head at adding the new one. So it's kind of like each time we add a new one, we add it to the front of the list. By my boat analogy, do you remember that crazy boat analogy where we're throwing bottles of Coke in the river, right? I take a bottle, I throw it overboard. Next time I want to add a bottle, I don't wheel all the bottles up and tie it to the bottom. I just tie the next bottle on and that one to the boat and throw it overboard. So each time you add one to the list, it gets added to the front of the list, so it ends up in reverse order. If you want to add things to the end of the list, Professor Malouf did that in the videos you should have watched for class. And essentially what you have to do is keep track of where the end of the list is. You can keep a separate pointer, and then every time you add, you put it on the end and then move the end of the list pointer down. Okay. So, boy, I went over that fast, didn't I? That was like I have some sort of ninja verbal stun capabilities by talking about pointers. People's eyes go. So, but if you want to add to the end, you essentially have to keep another pointer. You call it like tail or something, and then every time you add to the tail and then move the tail pointer over. All right, you can see that in the videos, Professor Malouf. You should know that for the exam too. Yes? Nope. No. But it's in the videos. It's in there. All right. So this part just created a linked list, right? And it created it in reverse order. Everybody good with that? I can't hear you. Yeah, the first thing that's pointed to is the last one out of the file. Does that make sense? So it's reverse order. If we traversed the list now using that loop that I showed you, that's like the while loop, it would print it out in opposite order that it came in. I'm talking about the order of this list if you were to traverse it from head to tail. Okay. All right, everybody good with this part, building a linked list? This is the easy part. Let's stop and think for a second though. What are we talking about today, if I haven't told you explicitly? Recursion. Recursion has two things. What does it have? A base case and something that you can split a piece off of. So let me ask you this right here. What is that right there? This is a linked list, right? We have a head and we have all these things hanging off of it. Is that a linked list? Everybody agree that's a linked list. I want 100% agreement. Everybody agree that this is a linked list. Let me ask you, what do we have right here? 2. We have a pointer to a linked list. This is the head, and it points at a series of things to chain together. This is also the head of a linked list. Is it not? How many of you all see that right here, this thing inside the node is also the pointer to a head of a linked list? How many of you all agree on that? How many of you are just raising your hands because I'm expecting you to? This thing is a linked list. This pointer points to a linked list. This pointer, what does it point to? What does this pointer point to? What does this pointer point to? What does this pointer point to? How about that one? It's a linked list. This is the empty linked list. It is still a linked list even though it's null. So what happens is we have a pointer to a linked list, but each thing on the list also contains a pointer to what? A linked list. Does this sound like something we can do recursion on? Why? Because we can take little pieces off it. Just like we worked in recursion before, you take a big problem, you work on one small slice of it, and then you hand the rest off to someone to deal with. We can do the same thing with pointers. We start with this big one, and what we do is each step along the way, we process one element, and then we call the function on the other linked list that's contained inside. Anytime you cut up a linked list, the rest of it is a linked list. Let's try that again. Anytime you take one of these things out of a linked list, the rest of it is? What linked list is this? The empty linked list. Okay? So we can do recursion on this. We can recurse over linked list. All right? So let's take a look at this code for a second. What does this look like here? Node thing equals do something head. We look at this function, node do something, right? And what does it look like there? List equals no. What do you think this might be? A base case. Absolutely. This is the base case. If the list is null, return null. Okay? Otherwise, we say if list get next node equals null, return the list that you found. Otherwise, do something on the rest of the list. So we have, what we have here is a base case, and we have a couple of conditions for doing something. Yes? Yes? Uh-huh. No, list is a parameter. It is a pointer to a node. Yes, we do. Because it gets called from right up here, and we say do something head. Yep. Sorry, I had to make the spacing better to get it fit on the sheet, but here is the recursive call right here. We say do something, and we pass it the entire list, because we pass it the entire list by giving it the head pointer. Everybody with me on this? What are the two things you need for recursion? A base case and a sliceable problem, something you can take in little pieces. Okay? And so that's what we have here. Every linked list contains within it another linked list. It is linked lists all the way down, okay? This linked list has this linked list, which has this one, what's this one? Which is also almost always going to be our base case. Our base case. So, everybody good so far? Everybody see conceptually what we're doing, even though we don't quite understand the code yet? Yes? We will talk through that in just a second, okay? All right, questions about the concept. Everybody understand now that we're doing recursion on a linked list. And it has the properties that we need, which are and. Okay, good. So we have a base case, which is going to be the null list. We have a sliceable problem. Let's take a look and see what goes on. So now we make this function call, and we say node star thing equals do something head. What is do something head? Right here. It's a function call. A function often returns thing. What is this function going to return? A pointer to a particular node. So our recursive call is going to do something over this list, and it's going to return a pointer to one of the nodes on our list. Okay? Does that make sense? Now, let's see if we can figure out which node it's actually going to point at when it's done. So here's where we start. Initially, we call node do something with the head pointer, right? So here's what happens. We have list. Originally, it comes in and it's pointing to head, right? Here's our list and it's pointing to head. Good with that? Because it points, when we say it equals something, it doesn't, this is not a node, this is actually a pointer to a node. So when we say a list equals head, it means point at the same thing that head does, not point at head. Okay? That's always going to be true, pretty much always. All right, does that make sense? Everybody good here? This is that first step right here where we pass head in as a parameter to the list. Good with that? All right, what's the next line of code say? It says if list equals null. Is it pointing at null? It is not. It is not pointing at null. Great. So now we say, we've passed this because list is null. We say if list get next node equals null. What does this list arrow get next node mean? We start at list. We follow the arrow, because that's what that arrow thing is. When we get here, we are looking at this node. When we say get next node, we are looking at this pointer inside the node. In essence, we are looking at the head of the next linked list. And we say, is this thing equal to null? It is not. So what do we do instead? We say return do something, list get next node. Okay, here's where it gets a little bit wacky. This one is our first invocation of the list, of the do something parameter. Next time we call it, what's going to happen is our second invocation will be pointing at that next one, because it is pointing at the same thing that list get next node was pointing at. Which makes sense if you think about it in terms of recursion. In terms of recursion, we work with one thing, and if the thing we don't find isn't there, we work on the other linked list that it contains. Does that make sense? So in essence, we have sliced this first thing off. It wasn't what we were looking for. And we've gone on to the other linked list that was contained inside. Who's with me? Who's against me? Who's not sure? Okay. All right. So here's recursion. The recursion was we looked at one thing, and we looked at one thing by saying if list get next node equals null, this is what we're looking for. And if we find it, we return something. Otherwise, we do something else. And the other thing we do is we call, for the second time, hence this 2 in front of the list, we call do something again. Yes? No? Maybe? Okay. Do you have a question? It's a pointer that points to a particular box. If you want to look at the pointer inside that box, you have to do arrow get next node to extract that data from the box. Yes, this pointer points at the entire node, not some particular portion of that node. We'll see. Trust me. We actually probably won't reach that in this example, but we can do something. We probably won't have time, but I can explain it to you quickly. Yes? Yep. And every pointer to a node in this is actually a linked list. Seriously? You are not changing list. What you're actually doing is creating another instance of list. Oh, come on, crazy computer. Ah! Yes, it is a long password. I am paranoid. And you know, the guys were here filming today, and they're like, I want to see you typing stuff. I'm like, don't film my password. Okay, so the call is, what creates the next list? It's the recursive call when we say do something here. Because when we say do something, just like before when we were calling function 1, it created a new copy of 1. We're creating a new copy of this do something, and we get a new copy named of something named list. Then let's just step through the code and I'll show you, okay? So here we are. Now we're in our second indication of list. We have this list pointer pointing at the node that has 4 in it. Let's step through here. Is list equal to null? It is not. Is list get next node equal to null? So here's how we check. We say list, follow the arrow, look in the box, get next pointer, get next node, excuse me. Is this pointer right here null? So what this is saying is list, arrow, get next node. It means from this list pointer, follow the pointer to the node itself, check the value inside get next node and see if it's null. Is this null? It is not. So what do? We call do something again. The third invocation points at the same thing this pointed at, right there. Everybody with me? So we just step through this code again. We have a new instance of list that points at the node containing the value 2. And what do? Is list equal to null? Is list, follow that arrow, look in here, get next node equal to null? It is not. So what do? We iterate again. No. List, get next node finds this pointer right here every single time, like it's done every other iteration of the loop. Okay? If you did list get next node, it follows the pointer here. It doesn't return this pointer, it returns this pointer. Trust me. Okay? Sorry, I'm running out of time. We have like 2 minutes and I want to get out of this. So we have a fourth instance of list. It points at this node. We step through our code again. Is list equal to null? It is not. Is list get next node equal to null? It is not. So what do? We recurse again. We get down here. List finally points at the node that has 16 in it. And we step in and we say, is list equal to null? Is list equal to null? It is not equal to null. List is not equal to null because this instance of list actually points at this box. So it is not null. So what do? If list get next node equals null, list get next node, look in here, is that null? It is. We found the thing we're looking for. And now what we're going to do is we're going to start returning this. We're going to start returning it. So what happens is this iteration of loop returns a pointer to there, which returns a pointer to this one, which returns a pointer to this one, which returns a pointer to this one. And when we're done, the thing that pops back out is this pointer to the last node on the list. What we have done here in this function, the do something function, should have been called recursively find last node. That would have been a better name for this function, recursively find last node. Because what we're doing is we're recursively going down the list until we find the last node on a list, and we know it's the last node because the next pointer is null. Does that make sense? Okay. For the exam, I will expect you to be able to do something like recursively find a particular value on the list, or something like that. Yes? This outputs 16, because what happens is when we return back to main, I'm sorry we're going a minute over time today, when we return back to main here, where did main go? Right there, we see out thing get data, and this thing is the pointer that's pointing to 16, the node that contains 16, so thing arrow get data follows that pointer and returns the data. Yes? It returns just once. Because what happens is each time it returns the pointer pointing to 16. So it returns that pointer each time, but here in main, it only outputs once. So it doesn't output each time. Yes? Yeah, we're kind of out of time. I'll go over this quickly at the beginning of next class. Okay, that's the best I can do for you now. Yes. We do, because what happens if the first time you call it, you're given an empty list? Otherwise, if you don't have that, it'll crash if you give it an empty list. And you know how I know that? Because when I wrote this, I forgot that case, and then I ran into an empty list, and it crashed.